my name is Ricardo, and I'm here with Math Matters, and today we're going to discuss probability, and especially the probability associated with playing the lottery. So, probability gets especially interesting when you talk about assigning money to it, right? Not only is probability interesting because you can find the random approximation of how often an event will happen, or how probable it is, how likely it is to happen, but when you assign money to it, you can actually calculate how much you can expect from the probability of an event to happen. So, like with the lottery, with this kind of probability, we discuss how much we can expect from a series of different events with series of different probabilities, each containing some kind of value assigned to them, or a dollar value, right? Money. So, usually with the lottery, there are several jackpots you can win, several different prizes, each with a different dollar amount and each with a different probability associated with them. So before we can talk about the lottery itself, and here we're going to use the Mega Millions as our specific example, we have to discuss a new concept of probability that we haven't talked about before, and it's called the expected value. So for the expected value, you not only need to have several probabilities, as in several different events happening, but you need to have values assigned to each of them, and that's usually money, right? So here I made a little chart. So if you have a probability of P1, the probability of event 1 happening, there's a value assigned to that event. So if this event happens, you get that money, or you get that value. Usually, we're going to talk about it as money. So if this is the probability of 2, and this is how much money you would get for that event happening. Probability of 3, how much money you would get for that. Probability of 4, how much money you would get for that, etc., etc., etc. I wrote all the way from 1 to 6. This is because we're going to talk about the expected value of rolling a die and playing a game that way. Okay, so usually when you have a value assigned to the probability, think of it as betting, right? If you bet on a horse race, you want to know the probability of your horse winning, and then it can kind of tell you how much you should bet, to tell you how much you should expect to win, the expected value of winning, right? So, with each probability and each payoff or reward that you get, or even bet that you place on that probability, there is a calculable expected value. So let's talk about these P1 through 6 as rolling a die. So you have a 6-sided die, and all of these probabilities are 1/6, because the probability of getting a 1 when rolling a die is, there's only one option out of 6 options, 1/6. Probability of rolling a 2 is also 1/6. Probability of rolling a 3, 1/6. All the way from probability of 1 to 6, each of those have a probability of 1/6. Because there are obviously 6 sides of the die, and you can watch my other video to explain how we get this probability. Now, let's say we're playing a game, and you place a bet on a side, and whatever side you place a bet on, that's how much money you're betting. So, for instance, probability of 1 has a value of $1. So that means if you land a 1, you get $1. If you land a 2, you get $2. If you land a 3, you get $3. If you land a 4, you get $4. If you land a 5, you get $5. And if you land a 6, you get the grand total of $6. So, big money, right? So this is because we're trying to simulate a lottery. And you're not always going to have the same value, right? Because if you had the same dollar amount for each different thing you played, it wouldn't matter what you rolled, you would always get the same value. So you want different values for your different probabilities. Because in this case the probability is the same. But in the lottery the probabilities are all different and the values are all different. But this example is a little easier. So, the expected value can be calculated. And it's actually the product of your probability and your value. So, whatever probability of 1 is, here we said 1/6, but we're not going to write that yet, times x of 1 is the calculation for your expected value of that event. But your expected value playing this game is the sum of all your expected values. So the sum of all your probabilities times all their corresponding values. And that makes sense because if you think of our probabilities, when do we add probabilities? When we have the probability of this event or that event happening. Probability of A or B is an addition. And expected value is the expected value of 1 or 2, or 3, or 4, or 5, or 6, where 1, 2, 3, 4, 5, 6 are our side lengths. So these probabilities are added because the probability of getting one of these is addition. As we said in our other video, probability of one or the other is addition. So expected value is probability of 1 times x of 1, where x is value, probability of 2 times x of 2, where x is value, plus probability of 3 times, let's just be consistent in how we write it, times x of 3, plus probability of 4, x of 4, plus probability of 5, times x of 5, plus probability of 6, times x of 6. Okay, but you get the point, because this could continue and continue, and it doesn't matter what they are. But in this case, all the probabilities are the same, and the values are pretty easy to memorize. Each value is the dollar amount of whatever side you rolled. Good, so let's calculate this. Let's calculate, if we played this game, how much could you expect to win? So, this is a very useful tool, because now you can, any betting game, you can calculate, if you know the exact probability and exactly how much money you would win, you can calculate the expected value of playing a game. So, let's do it. Probability 1, this is 1/6, all the probability is 1/6, times 1 for the first one, plus 1/6 times 2, plus 1/6 times 3, plus 1/6 times 4, plus 1/6 times 5, write that a little lower, times 5, plus 1/6 times 6. Okay, so here are all our expected values. Okay, I'm not going to write it out again, but let's just take out our handy dandy back pocket calculator and calculate this out. So 1/6 times 1 is 1/6, and then 2/6 times 1 is 2/6, so we're adding these together. 1/6 plus 2/6 plus 1/6 times 3 is 3/6 plus 1/6 times 4, 4/6, right? And you get the idea, 5/6 and 6/6, or 1. So you add all of these together, and you get 7/2, otherwise known as 3.5. So if we're doing numbers, and we're doing dollar values, not numbers, we're doing numbers because they're values, but if we're doing dollar values to these things, we're assigning dollar values to these things, you can expect the value of $3.50 from playing this game that I just made up. Okay, now that's a very important number. At first you may think, well, that's pretty random, who cares, right? But what if I say it costs $4 to play the game? Okay, well if it costs $4 to play the game, and you know your probability, you would say, no, I'm not going to play that game because I am expected to lose 50 cents every time I play the game. Now, obviously this does not mean you're going to lose 50 cents every time, but on average, if you played 100 times, you'd expect to have lost the equivalent of 50 cents every time you played it. That's because probability can't tell you what happens every single time. It's a random event. There's no way you can find that out. Probability just tells you the likelihood of something happening and how probable it is over a large sample. Good. So how does this relate to the lottery? Well, the lottery is a little more relevant. Because if you can consider, I have data from the North American Association of State and Provincial Lotteries. But it turns out that in 2012, the US federal government had $78 billion in lottery ticket sales. Not bad, right? But then consider how much of that money goes to the government. That's 25% of the government is taken in as revenue, of the money is taken in as revenue by the local state governments. So, for instance, New York led by selling $6.2 billion in lottery tickets, and that was about $1.6 billion just in revenues from these tickets. And, I'm assuming, most of these people did not calculate the expected value of purchasing lottery tickets, and in some cases, had they done it, they might have not spent that money. And it's just relevant because when you think about, if you can invest $1 million in lottery tickets, you'd expect eventually you'd win the jackpot, right? But with the sheer multitude of lottery tickets there are, you might not even win with $1 million just spent on lottery tickets. And probability gives you these big numbers, so if you decide to invest in lottery tickets, you should know if you're expected to gain from investing that much money? Or if you know you're going to lose that much money, why would you ever invest in lottery tickets? And why don't people do that? And that's what you can find out here. So we're going to do a quick calculation. Now, I'm using the Mega Millions, and in the Mega Millions, just a cool tidbit, the way that game is played is there are 6 numbers you have to choose. 6 different probabilities, or 6 different probabilities to make up the giant probability. And the first number is out of 75 times the next 5, which are all out of 75. Rather sloppy, but the first 5 are out of 75. If you get all these right, and you're still not getting the jackpot, because there's a Mega Ball, or the Mega Millions special number, which is out of 15. So there's another number out of 15. And if you get all of these right, we multiply it because probability of all of them is probability of 1 and the next and the next and the next, which is multiplication. Multiply them all out, you get, the odds are about 1 divided by 34 billion, or 1 in 34 billion tickets. Now, that would mean about 146 tickets purchased per each legal adult in the United States. And that makes no sense, because no one buys that many lottery tickets, and definitely not that many lottery tickets are sold, because that's more than the amount of people in the world, 34 billion. So this is a huge, insane probability by itself. But luckily, it's eased down on you. It's not out of 34 billion, it's out of 258 million. 258,890,850 to be exact. So the odds are 1 in about 258,259 million. That's because 259 million tickets are sold. It can't be out more than that if there's only that many tickets and somebody won, right? Or somebody's winning. And this is a lottery that already happened, so yes, somebody did win out of these 259 tickets. So when I say 1 in that many, this is the number that's important. The 1 in is obvious because there's only one ticket that wins out of this. So I'm just going to say 1 in from now on. Now 1 in 259 million. That means 259 million $1 tickets were bought. So if you spent $1 million, you would have 1 million chances. And that's still 1 in 259, 1 in 258. So it's not a guarantee. You would spend $1 million in lottery tickets and be nowhere close to lottery. But the jackpot, so lottery jackpot is what I meant, but the lottery jackpot is not it, right? You could also win lower prizes. In fact, the second prize is $1 million. Hey, $1 million is not bad, right? But the probability of winning the jackpot is so very low that when we calculate the expected value, probability times the jackpot, it really doesn't contribute to the expected value, to the total expected value. So, for a calculation of the expected value, we do probability times the value. Now, the value in one of the highest record lotteries ever, Mega Million lotteries, was $636 million. So $638 million jackpot. Multiply that by 258 million and all the other probabilities. So everything from 636 million to, I believe there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 options that you can get, and the lowest being you get $0, right? So you can get 0, 1, 2, 5, 5, 10, 50, 100, 5,000, etc., 50,000, a million, 636 million. All these options. Now, it's very interesting to think that the 10th option, x of 10, which equals $0, has a 93% likelihood. So it's not even 1 in something, it's just 93% of the time. I mean, it is 1 in something, but the number's not as nice and not as compelling as saying 93% of the time you get absolutely nothing. And this is actually losing $1. You don't just get nothing. You spent $1 and now you lost it, and it's gone. So when we calculate the expected value, this falls to not only to 0, but to -1. Because the expected value is your profit, right? How much would you profit from this? You profit $1. So therefore we're going to do the expected value. I'm going to call it EV, which is probability of 1 times x of 1 all the way to probability of 10 x of 10. So this is 1 in 258 million over times 636 million, plus something else, plus something else, plus something else, all the way to -1 times 0.93, right? So it turns out your expected value for this record high lottery, this is, if you're ever going to invest in the lottery, this is the time to invest, is $1.62. $1.62. That is more than $1. So if you want to invest $1 in that, you're gonna have a profit, and that's a very compelling argument, and people pay attention to that. That doesn't slip by unnoticed. People notice that. Now, let me clarify. If you disregard the lottery, if you disregard the lottery jackpot, rather, if you disregard the jackpot, take away this first term, the expected value of the rest, let's call it EV2, is about like 82 cents. So yeah, the jackpot matters. If you ignore the jackpot, it's very unlikely that you're going to ever invest. But, so why don't people invest? Why don't people invest in the lottery? Why isn't that something that you've heard about? Well, it's because people don't invest in that lottery. Because the lottery is offered in 2 payment options. You can either get about a 30-year annuity, which means you get a smaller sum every year for 30 years, and therefore you can't really count your profits as 636 million. It's more like that divided by 30, how much you get in 1 year. Or you can take it right away, and you get about half of it. So getting about half of it, and once we realize how important the jackpot is, getting about half of it is pretty depressing, because now when you calculate your expected value, the jackpot is half of what it used to be, and it takes away quite a bit of your earnings. In fact, your expected earnings goes down to about, let's see, $0.49. So, without the value of the Mega Millions at 636 million, and instead it shows here you would get about 341 million, the expected value is only 49 cents. Now, it's still a viable option, but the profits you get are not nearly as satisfying as $1.62, and because we compensated for the $1 that you spent buying the ticket, this 49 cents is not even half of that. So getting a profit that's not even half of what you invested, and if you bring this to the millions, investing millions of dollars, getting a profit of not even half of what you invested is not something that's worthwhile, and that's why people don't really invest in the lottery. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video of my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.